Srimati R. Padmavati, Head of Department EC, Dhanalakshmi Srinivasan College of Engineering and Technology, Chennai. She pursued her Bachelor of Engineering in Electronics and Instrumentation Engineering at the National Engineering College, Kovilpatti. She then went on to work as a technical editor in Domix Technical Information Private Limited, Chennai. She then pursued her Masters of Engineering in Applied Electronics at Satyabama University, Chennai. She is currently pursuing her PhD in Anna University, Chennai. She has published several national and international journals and has attended many conferences. Her areas of interest include linear integrated circuits, digital electronics, electronic circuits, VLSI design.
Welcome to UGC lecture series BSc Electronics Honours for the subject Analog Electronics. Today we are going to discuss about the relationship between alpha, this is the current amplification factor for common base configuration, and beta is the current amplification factor for common emitter configuration. An operating point of bipolar junction transistor BJT, stabilization factor of BJT, fixed bias circuit and emitter stabilized circuit, comparison of fixed bias and emitter bias circuits, and finally load line analysis. So, now we are going to derive a relationship between the current amplification factor alpha and beta. So, what is beta? It is the current amplification factor for common emitter configuration. So, in the previous classes we have seen the common base, common emitter and common collector configuration and the input output characteristics of all the configurations, where we have seen what is beta, what is alpha. So, beta is the current amplification factor for common emitter configuration. So, it is the ratio of the output current to the input current. In common emitter configuration, the output current is the collector current and the input current is the base current. So, here IB can be written as IC by beta. And what is alpha? Alpha is the current amplification factor in common base configuration, which is the ratio of the output current to the input current. So, in common base the output current is collector current and the input current is the emitter current. From here IE can be written as IC by alpha. So, IB is also in terms of IC, IE is also in terms of IC. Now, you substitute in this equation, it is the common equation for all the configuration. Whatever the configuration may be, the emitter current is the summation of the collector current and the base current. You substitute it here. What is IE? It is IC by alpha. IC by alpha, and here it is IC plus IB is IC by beta. IC by alpha is equal to, take IC out. So, you will be getting 1 plus 1 by beta. So, IC can be cancelled out, 1 by alpha is equal to, if you take LCM, beta plus 1 by beta. So, what is alpha? It is beta by beta plus 1. So, this is one relationship. You can also derive, this is alpha in terms of beta. You can also derive from the previous equation IC by alpha equal to, if you take IC out you are getting 1 by 1 plus beta. So, from this equation it is IC by alpha equal to IC into 1 plus 1 by beta. If you solve this, 1 by alpha equal to 1 plus 1 by beta, 1 by alpha minus 1 equal to 1 by beta. So, take LCM here, 1 minus alpha by alpha equal to 1 by beta, and what is beta now? Beta is alpha by 1 minus alpha. So, this is beta in terms of alpha. Previously, we derived alpha in terms of beta. And one more equation we have studied in the previous sessions, that ICEO is equal to ICBO by 1 minus alpha. This can be written as beta plus 1 into ICBO. For that, you have to obtain an derivation to replace this 1 by 1 minus alpha as beta plus 1. So, we are having beta equal to alpha by 1 minus alpha, beta equal to alpha by 1 minus alpha. If you put beta plus 1, it is alpha by 1 minus alpha plus 1, both the sides add 1, take LCM. So, you are getting beta plus 1 is equal to 1 by 1 minus alpha. So, you can replace this 1 by 1 minus alpha as beta plus 1. We all know that what is this ICEO and what is this ICBO. It is the current, leakage current when emitter is open. It is the leakage current, ICEO is base is open, leakage current when base is open, and ICBO is the leakage current when emitter is open. ICBO is in common base configuration and this ICEO is in common emitter configuration. So, we have derived a relationship between alpha and beta, alpha in terms of beta as well as beta in terms of alpha. For further derivations, we have to have this in mind, that beta is alpha by 1 minus alpha and alpha is beta by beta plus 1. And next is quotient point. While we discuss about the diode configuration, we have seen what is a quotient point. It is a Q point, it is otherwise known as Q point. Always you can say this as an operating point. So, what is a Q point or quotient point or operating point is the transistor. In the output characteristics of the transistor, we have to find the Q point in the linear region in such a way that the transistor must produce the maximum excursions in the positive and the negative directions of the input signal without any loss. So, for that the Q point, the DC load line is important and the Q point is important, and Q point which is a fixed point, and so it is known as, it is the quotient means quiet, still, inactive. Since it is a fixed point, the name is quotient point, which means that quiet, still, inactive. Biasing small signal amplifiers. So, you have to choose the Q point after biasing the amplifier. So, the Q point should not shift because of the change in the collector current, because we know that the Q point is selected in the output characteristics of the amplifier, and in output characteristics it is drawn between the output voltage VCE in the x axis and IC in the y axis, and Q point is somewhere in the output characteristics. So, this Q point can be located with the help of this IC and VCE. So, this IC is a major factor to locate this Q point, and it should not shift because of the change in IC. This IC, the collector current, will vary depend upon the temperature and will vary according to the replacement of the transistor. So, we have to select the Q point first. So, this is the output characteristics of an amplifier. So, this is the in x axis it is plotted for VCE, that is the output voltage, and in y axis it is the output current in milliamps, it is the collector current. And here are a few operating points located in the output characteristics A, B, C and D. So, we have to see which operating point is linear one or which operating point is going to give you a linear output or the maximum output for both the swings, the positive and the negative swing of the input voltage. And we know that in the output characteristics we have already seen where the saturation region exists, where the cutoff region exists and what is the active region also. So, this is the saturation region, it is the VCE less than V saturation value, VCE saturation value. The saturation region exists at this VCE less than VCE saturation, and where the cutoff region exists it is below IB equal to 0 microamps. Always we know that the IB current is in the range of microamps or in some cases nanoamps. So, below this IB equal to 0 we will have the cutoff region, and here this is the active region. So, we know the basic assumption that the operating point must be present in the active region. We will see these operating points one by one, whether which one gives you the maximum excursions for the output. What is this point A? This point is located at 0 level. So, before biasing we did not give any bias to the circuit. So, if you choose this point there will not be any change in the output with respect to the input because it is already in 0 level. So, we have to give bias first for the transistor. So, if you choose this point, the point C, it is closer to the 0 level. When you look at the current, it is closer to 0 level, and for the voltage also closer to the 0 level. Can you imagine this point is going can be able to give you the maximum excursions for the input output swings, the input swing in the positive region as well as in the negative region? It will not be possible because it is limited by VCE 0 and IC 0. The peak will be clipped away if you choose this operating point as the quotient point. And what happened to this D, this point D? It is closer to the maximum value. See here, this is the VCE maximum. So, beyond which we cannot give any voltage to the transistor. This is the maximum value of the output voltage, and here this is the maximum current for the transistor, beyond which the transistor cannot withstand. So, if you choose this operating point, the maximum voltage, it is closer to the maximum voltage. So, this point will also be not opt for the operation of the transistor as an amplifier. Again the output cannot be a amplified output of the input signal because it is closer to the maximum value of the output voltage. Again there will be a clipped condition. So, we will not be getting any proper output signal at this point also. And when you look at this B, it is middle of the active region, and also the IB value is uniformly distributed in this range. It is not closure, and it is not close to the 0 level or as well as to the maximum level. So, the output will not be clipped off because of 0 as well as at the maximum value. So, this may be the opt quotient point. At this point the transistor will give you maximum possible swing for the positive side as well as for the negative side of the input signal at its output terminal. So, in this way you have to select the operating point of the transistor. Once you selected, this operating point is fixed, and so it is called as the quotient point. and if it has to be fixed, we have to have these points in your mind, that the operating point should not shift because of change in IC, and this collector current IC will change when you change the transistor or the temperature changes. So, what will happen if these two conditions arises? The current gain and the leakage current is dependent on the temperature. If temperature changes, then these two factors will increase, and higher the temperature result in increased leakage current. So, we must have a stability network, the temperature stability network with the transistor to have a fixed operating point or minimum change in the operating point. What do you mean by stabilization? The process of making the operating point independent of the temperature changes or variation in the transistor parameters. It is necessary due to the temperature dependence of IC, individual variations, that is, if you replace the transistor, then there is a condition called a thermal runaway. We will see it now. The temperature dependence of IC, that is the collector current. We all know that the collector current is the summation of the majority, the current flow by the majority carriers and the current flow by the minority carriers. This ICBO is the leakage current, and when the temperature increases of about 10 degrees Celsius, then the leakage current doubles. For every 10 degree rise in temperature, then the leakage current doubles the value, and the ultimate the collector current will increase. If the collector current increase, then the temperature, the heat field in the transistor is high, and if it is high, then again the temperature increases, and for the increase in temperature, ICBO will also increase, and again IC is increasing, and so this is a cumulative process, because of which there is a condition, the self destruction of transistor happened, and this self destruction of an unstabilized transistor is known as the thermal runaway. So, we have to have a temperature stability circuit in the amplifier circuit for reducing the temperature because of increasing the collector current in the transistor, for which heat sinks will be provided in some of the circuits, or a fan, cooling fan can be used in the amplifier circuit. And so, we have to deal about the stability factors, the rate of change of the collector current IC with respect to the collector leakage current ICBO, change in the collector current with respect to change in the leakage current. If S is low, then it has a better stability. So, we have seen the region of operations in the previous sessions, that in the linear region, base emitter junction forward biased and base collector junction reverse biased. That is, the input junction, whatever may be the configuration, the input junction must be reverse biased and output junction must be forward biased. Cutoff region, for which the input junction must be reverse biased. For the saturation region, both the junctions are forward biased. So, once the bias is given, then we have to choose the operating point, and we have to stabilize the operating point at a constant value, for which you have to have a bias circuit, so that we can find out the stability factor of this particular circuit, and finally, we had a conclusion of which bias circuit is preferable for stabilizing the amplifier circuit. So, there are a variety of bias circuits for the transistor, and all the circuits have different stability factors. So, now this is not our point of discussion here, fixed bias circuit, but we have to compare the self bias, that is the emitter stabilized bias. This is the important circuit which we have to discuss now. So, to compare this emitter stabilized bias, we are having one more bias circuit as a fixed bias circuit. So, this is the circuit diagram of fixed bias circuit. Here RB is connected between the supply and the base terminal. So, through this RB, by choosing this RB, we are going to fix the stability factor. So, the RB is the important parameter in this fixed bias circuit. So, here from this circuit, if we derive the stability factor, that is IC, the change in the collector current with respect to the change in the leakage current, it is derived as 1 plus beta, high value since beta is very high. So, what we have seen, if the stability factor is lower, then it has a better stability, but it is in terms of beta. So, the stability is higher here. So, it has S is higher. So, it has a least stability. So, we are moving for the next biasing circuit called emitter stabilized bias circuit, which includes this emitter resistance in its emitter terminal of the common emitter configuration. So, there is the only difference. Here there is no emitter resistance. Here we have included a emitter resistance to have a better stability than the previous circuit. So, we have to examine the input loop and the output loop. Input loop is the emitter base loop and output loop is the collector base loop. We have to find out the IB current, since it is a IB current is going to reflect in the IC current now. So, this is the base emitter loop. This is the base emitter loop. When you look at this circuit, we have not taken this capacitor here. So, only we have taken the resistance part, we have neglected all the capacitors here. So, this RB is given supply VCC and it is connected to the base terminal of BJT. So, RB is connected to VCC and other end is grounded, and the other end of the resistor is connected to the base. Since we are considering only the input loop, we just close the input loop only now. So, now we apply KVL to this input loop, VCC minus IB is the current flowing through the resistance RB. So, VCC minus IBRB minus VBE, that is the voltage across the base emitter terminal, minus IERE equal to 0. So, by using Kirchhoff's voltage law. So, from the relationship between alpha and beta, and from the KCL IE is equal to IC plus IB, and also from the collector current, it is due to the majority carrier flow and the minority carrier flow. When you substitute the equations in this collector current, you will be having a relationship between IE and IB. You can obtain, you can try this. How will you obtain this IE equal to beta plus 1 into IB, for which you have to know what is the collector current IC in common base configuration, that is all. So, you can use the relationship between alpha beta there and you can derive this equation easily. So, now you substitute it for IE, it is VCC minus IBRB minus VBE minus beta plus 1 into IB equal to 0. So, when you take out this IB minus IB, RB plus beta plus 1 minus VBE equal to 0. So, find out what is IB. IB is equal to VCC minus VBE by RB plus so here you must include RE, because for this part beta plus 1 IB is substituted and RE you have to write it, and so here R E beta plus 1 into R E. So, this is important equation in the input loop of the base emitter loop of the common emitter configuration. So, what we have substituted here for IE beta plus 1 IB. So, after substituting and after simplifying it, you are getting IB equation here. So, when you look at this equation, it is this term is included in this equation. For fixed bias, the previous circuit, if you derive IB, it is only VCC minus VBE by RB. But in this case, we are getting an extra term beta plus 1 into RE because of this RE resistance in the circuit. This RE is the resistance we have connected in the circuit, for which you are getting beta plus 1 RE. So, beta is very high. So, the total term is also very high. So, this is the equation we have derived. For this equation, if you draw a circuit, it is the current IB, it is the current IB flowing from VCC to VBE. So, VCC to VBE through the resistances RB plus RE resistance. So, RB plus RE resistance, where this RE resistance is multiplied with a factor of beta plus 1. So, this is what we are getting for the input side. So, the input resistance, the reflected impedance level of RE is seen at the input side, that RI is beta plus 1 into RE. This is what we have derived for the input loop, and for the output loop, we know that from the circuit, if you see, this is the only part present in the output loop without this capacitor RC, RE and VCC. So, we have connected this RC, RE to VCC. So, for this, if you apply KVL again, VCC minus ICRC minus VCE, it is the voltage between the collector and the emitter terminals, minus IERE equal to 0. So, we know that IE is approximately equal to IC. So, replace IE as IC into RE equal to 0, and if you take IC minus IC out, it is RC plus RE minus VCE equal to 0. And what is VCE? VCE is VCC minus IC into RC plus RE. This is the one of the equation from which you can obtain what is the operating point. When VCE equal to 0, find out IC. When IC equal to 0, find out VCE. From this equation, you can obtain what is the operating point. And if the question is what is VE, the emitter voltage, it is IE RE. Otherwise, you can write it as VCC minus VCE. And what is VB? It is VBE plus IERE. These are some of the important equations from this output loop, and this is the output of the fixed bias and the emitter bias configuration, fixed bias and emitter bias for common emitter configuration. If beta is increased 100%, what is happening for IB current, IC current and VCE? IB is same and IC is doubled and VCE is reduced by 76%. When you see it for emitter bias, when beta is doubled, that is 100%, if you change it, IB is reduced slowly and IC is increased to stabilize this IB. and what is VCE? It is dropped to about only 35%. So, when you compare these two observations, the emitter bias is more stable than the fixed bias for the same value of beta. And load line analysis, this is the common emitter configuration here. These CS, CC and CE or the coupling capacitor, CS and CE or the CC or the coupling capacitors, and this CB is the bypass capacitor. So, the current AC current will flow through this capacitor so that it bypasses this resistance RE. And when you look at the graph, if you bias the circuit, the input current will swing in the same way as the input, and also the output current IC and IB has the same waveform, but what happens to the output voltage is reversed because the IC is increased, IC current is increased here, and so the drop at the output will be reduced, and so for the positive swing the output will be in the negative side. Similarly, for the negative swing the output will be in the positive side. So, there is a 180-degree phase shift between the input and output for common emitter configuration. And when you look at the load line analysis, so this is the DC load line. DC load line is drawn from the DC equivalent circuit of this voltage divider bias circuit. Voltage divider in the sense R1, R2 are the voltage dividers through which we are biasing the circuit, common emitter circuit. So, it is a voltage divider bias circuit. So, when you draw the DC equivalent circuit, there is no capacitors for the DC equivalent circuit, and when you look at these resistors, it is series RC and RE are in series. So, the DC slope has -1 by RC plus RE. So, you will have the Q point at here as well as at the x axis here. From this DC load line, wherever it intersects the IB curve, you will have a Q point. And when you look at the slope of the AC load line, this is the AC equivalent circuit from which you have to find out the slope. It is RC parallel RL. So, -1 by RC parallel RL. So, the current will be maximum if the resistance value is increased. So, somewhere over here you will be getting the point ICQ, the point for the AC load line. So, here you have drawn the AC load line. So, it is moved slightly towards the saturation region when you compare it with the DC load line. So, for the DC load line you have to draw the DC equivalent circuit and find out the slope. For AC load line, AC equivalent circuit is drawn and the slope is found out. So, when you compare these two, the DC load line has the maximum resistance and the AC load line has the minimum resistance. So, it has a maximum flow of IC here. So, we have seen in this session the relationship between alpha and beta, the operating point, stability of bipolar junction transistor, comparing the fixed bias circuit and emitter bias circuit with various factors IB, IC and VCE, and finally the load line analysis. Questions to refresh your understanding: what are the factors affecting the stability of Q point in BJT? What is thermal runaway? How do we have a stable operating point, and what is AC load line? These are the references. Thank you.